everything you learn in this class, and count 2 and count 3. Every count, you just add another variable. In count 2, you have 2 variables. In count 3, you have 3 and more variables. And then you follow this idea again. You follow this pattern. You're going to study limit with 2 variables in count 2. Okay? You do everything like this, then you're going to have different quotient again. I've been teaching count 2 for a couple semesters already. Count 3 the same. Same idea. Start with limits. But limits have 2 variables. And then you move on to derivative, 2 variables. Integral, 2 variables. And application of them. So that is count 2 and count 3. Okay, in count 3 you add another variable. Okay, so it's going to be just more complicated. But the frame is that there. Okay. All right. Let's proceed. Velocity. Average velocity. Average velocity. Velocity. Normally, okay. Anyone in here decided your major that you're going to be physics or STEM major, right? So yeah. What would be the idea behind velocity? Normally, don't think about calculus. Normally.
Instantaneous, like rate of change.
Rate of change. And how do you actually usually find that? Back in physics class, maybe high school. How do you find? Huh?
The rate times the time.
The
Rate times the time.
rate time. Say again.
Rate times time.
Rate times time. Okay, that is the unit. That's a unit. That's a unit. Rate times time. That is technically the unit of velocity. Something more. Okay, I'll give you a hint. Relate to distance. Go ahead.
It's the derivative of your position, right?
Speed.
Drop the calculus. More. I want you to. Okay, Okay, this is a good time to try to speak math, explain math, in a way that a high schooler, a secondary student can kind of understand you. Okay.
Speed. It's a change of distance over change of time. Right?
Okay, change of distance over change of time, right? Distance over. Okay, shorter. Try to explain shorter in a shorter version. Just distance over time. Okay, just distance over time, right? Distance divided by time. Okay, maybe I put there. Okay. Distance, usually in physics they use S or D, right? Time is T. Okay. Yeah. Distance over time. And then the velocity at time T, it's just gonna be the limit. Okay, actually, we know that's a limit. Leave it there. I'm gonna derive the limit for you. Distance. Okay. Let me draw a small diagram. Okay. Distance. If I have a distance function, it's like this. There. Oh, actually from here to here, easier. There. This is S. This is T. So this is T1, T2, right? S1, S2, right? Right? X1, S2. And from here, I move into here. How long does it take me? From here, okay? Maybe 1 second, 2 seconds, 3 seconds, right? Time. I move how far then? I move 1 meter, 2 meters, 3 meters, and so on, okay? So this right there, right? So the velocity, with the velocity of this one, is the rate, technically the slope of this one, right? The velocity in this problem is the slope of this line, right? The velocity is the slope of this line, which is, remember the rise over run? x2 minus x1 divided by t2 minus t1, right? Rise over run. There. And if I use the different quotient, actually put it here, S of T2 minus F of T1 divided by T2 minus T1. Okay. Therefore, you have the different quotient S of t minus h minus f of t divided by h. These two basically the same. Yesterday I showed you that. Okay, you change the variable. You have this expression exactly the same. This expression. Okay. Okay. So that's how you find velocity. Okay. Using this. Okay. If you use this one, you find the time, the velocity at one time, one specific time. Just one, exactly one time. Okay, maybe 2 seconds, 3 seconds, 5 seconds. It's called instantaneous velocity. Velocity at a specific time, that formula, right? But if you use this one, the one with the limit, same like above the previous problem, you find the velocity everywhere. Okay, so even this one is more general, more powerful than that one. Why is it more powerful? Because you have that limit in the front. Okay, you have the limit in the front, you put the limit in front, and here you have the velocity at everywhere. Okay, so just plug in the time. I want to find the velocity at 5 seconds, plug in 5. I want the velocity in the beginning, plug in 0, and so on. Here, you know exactly at one place, one time only. You can only use it once. Okay, so this is the one to go to. Okay, similar to the tangent line, this is the one. Okay, apply. A ball drop at the height 400 feet the meter above the ground with the following position equation. So you have the position equation is 4.9 t squared. That basically g over 2, right? Assuming downward is positive direction. Okay, so therefore, this is just a physical notation. That means this is positive. That means your velocity will be positive. Yeah. Okay. And for this problem, you may, okay, I make a little bit, mistake in the spacing. There should be a big space in the middle. So this space down here on the handout will not be enough. So be prepared to get a scratch paper or attach something or write on the other side. Huh? Okay. Okay. So technically you need more space. Okay. One by one. What is the velocity after 5 seconds? In order to know what velocity after 5 seconds, first thing first, find velocity at any time t first, the general first, right? And then you plug in 5 seconds. Plug in 5, you get your velocity at 5 seconds. Find the velocity at any time t. How do you do that? Remember, velocity is similar to tangent line. Velocity or the slope of tangent line, they share the same formula. It's just the limit of the different quotient. So the velocity right here at any time t is just the limit when h approaches 0 of the different quotient right. Use this. Okay. How about you try this, practice this. You have your S of t right there. You have this down here. Now you just have to plug in t minus h there. Expand that, simplify, make sure your goal, what's your goal? What is your goal in this problem? In this particular problem, in terms of algebra, what would be your end goal? Yes, eventually you solve for t, but in order to do that, in order to bypass that limit, you don't want the limit, right? You want to solve for this limit. In order to bypass this limit, what do you need to do?
Something other than h in the denominator.
Yes, you cannot plug in the 0, right? You need to plug in zeros in this. But right now that h is on your way. So you're going to simplify, you're going to do some math until you cancel that edge. Try that. In the meantime, I'm going to throw in another page. Okay, practice that now.
So the session is squares. So you're just taking the derivative of that. So you can take the thing of the velocity at any point. You already know. That's t plus t.
Okay, when you plug in, you should have that, right?
Can tell you the velocity.
What did you get for your answer?
I got 49 meters per second.
Yeah, and I just didn't put it in, but I got the same. So you put in the 0 and then put in the 5.
Okay. Let me give you the expanded version. Okay. How do you expand this one?
4.9 t squared. Oh, shit.
Okay. Let's yes, yeah. You're gonna distribute it, right? So t squared plus 2th plus h squared minus 4.9 t squared. Okay. This part right here, I believe this is where you feel hiccup, right? If you, okay, recall this formula. Perfect square. Sum. Square of a sum. There. That's what I just used. If you don't know that, if you don't recall that, then you can do this. Right? You can do that, and then what do? Just distribute term by term. You will end up this one. Okay. So that is what I did over here for this one. Okay. All right. H on the bottom. H on the bottom. Distribute 4.9 1 by 1. 4.9 times 2, 9.8, right?
Yeah.
TH, another 4.9 minus 4.9 t squared divided by h. Luckily, we have that is plus, that is minus. Okay. At the same time, you see that these two terms, each one of them has the h. One h here, two h right there, h squared technically. So you're going to cancel with this one. You're able to cancel it now. So I cancel this, and that is the purpose of this problem, right? Cancel the h on the denominator. Okay. Keep going. Oh, no more fraction, because no more h on the bottom. So you only have 9.8 t plus 4.9 h. And now you're able to plug in the 0 without a determinant. Just 9.8 t. Right, 0 here, this term goes away. Right. So that, there you go. This is the velocity. This is the velocity at any time t. Then the question asks you, at exactly 5 seconds, how fast is it? So at 5 seconds, or after 5 seconds, that means t equal 5, then the velocity of v sub phi, right? You're going to plug in phi, v sub phi. V sub t is that, v of phi going to be 9.8 times phi, which is 40? 49 or 5? 49. Okay. We are doing more or less like physical problems. Physical problem. Always need unit. What would be the unit of this problem? Yeah. Everything in terms of meter right here. The question is 5 seconds. So the unit would be meter per second. Okay. So after 5 seconds, the ball was moving at 45 meters per second. Okay. Now B. How far until it hit around, or how far it travel technically? Okay, copy that. That's the question. It's for 50 meters, right? How fast? My bad. Okay. Apologize for rule number 5. You want to redeem it? How fast?
The velocity is what we're looking for.
Okay, the velocity, correct. Thank you. How fast? When it hit the ground, to be correct. Until. How fast when it hit the ground? Okay. How fast it goes when it hit the ground? How do you do this one? Think. Now discuss. Maybe a minute or two. And try that. Play around with that. Solve this. Okay. Try that. So now we know that we're looking for v sub t when it hit the ground. The key word is right in here. When it hit the ground, what happened? First of all, you have to understand the question. When it hit the ground, that means it's the moment right before it hit the ground. Not when it actually hit the ground. When it actually hit the ground, that is technically stopped, right? Velocity is going to be 0. Nope. Just a split second, 0.0001 second before it hit the ground, still have a small gap, really small gap right there. So that, when at that moment, it has some velocity. What would be that velocity? That is the question. Okay. So first of all, it will not be 0. So you can eliminate that option. Not 0.
That's what I was thinking.
Okay. Any idea? How do we approach this one? Go ahead. Group 2, right? Group 2, right? Okay, go ahead.
Use the general slope form, the general slope, so use 9.8t.
Correct. Okay. You're going to use that for sure, yes. So this, right now we found out that is 9.8t. Okay. What can we do with this? Yep, that is the start. This tells you the velocity at any time t. The velocity as a function of t. So to find the velocity, this is what you're going to use to find. But in order to find the velocity, in order to get some number, what do you need? The time. You need the time. You need some time to multiply by 9.8 to get the velocity. Then, when it hit the ground, the time that you're looking for, how do you explain that? How do you describe that time? Curve down.
Time out there draws 450 meters.
The time when it hit the ground, right? The time it traveled 490 meters. The time it hit the ground. The time it hit the ground. Then now my question for you is, when is that? When does it hit the ground? Okay, so this is what you're looking for. In order to solve for the velocity, you need the time t hit the ground. In other words, that is also the same time you travel 490 meters. Okay. Somehow explain it in another direction. Okay. It traveled 400. That is the distance. So when it traveled 450 meters, how long it traveled 450 meters? That is what I'm looking for. My bad. Not 0. Okay, sorry. It starts from 0 technically. It goes 450 meters. How long does it take? Okay, now solve for t. Okay, when you solve for t, plug that in v sub t, then you get the answer. But when you solve for this t, how many t do you end up with? How many t you end up with? T squared, and then you're going to have, check the square root, how many t you have? Plus or minus. Explain the plus or minus.
Oh, well, like we have like a negative number, like let's say -2. -2 squared is 4 because negative times a negative is a positive. So anytime that you have a square root, there's also a negative answer that equals the same thing.
Okay, equal the same. But in this context, do you use that negative number? No, because that is time. So you only need the positive number. Okay, so solve for that t. Whatever you have over here, only keep the positive. Then plug in the velocity at t equal whatever that number is v sub okay, finish that. Down there, right? 9.58. Okay, so let's round that up. 9.6. Next box is 9.6. When t equal 9.6 seconds. So V is 9.6. So I have 9.8 times 9.6, which is, finish that. Still, group 3, finish that. How much?
It's about 94.
94, about, okay. 90. Okay, there you go. Everybody have the same answer? All right. Okay, so that's how you use limit of a different quotient, okay, to find the velocity given a position or distance. Okay. Last thing, derivative. Okay, let's make a connection in the concepts that we learned so far. Recall both tangent line and velocity involve limits with basically the same formula, right? Limit of a different quotient. Both of the concepts tell us the rate of change, or how fast, and how fast is basically velocity of a curve at a point. That statement is not really correct. This statement not really correct. Not just at a point, and everywhere else, and everywhere. Remember this, in the hyperbola, you find out that the slope is negative 3 over x squared for the hyperbola. You have the slope is like that. And then when you, that is the tangent line. When you, the problem that we just did, 4.9 t squared, that's the distance. Then you're able to find out the velocity at any time t, 9.8 t. Those two examples from yesterday and today, this and that, tell you the rate of change. It's really fancy word, basic word. How fast or how the function behave throughout, everywhere, not just at one point. At one point, then that's where you plug in t equal whatever the time, right? The 9.6 something. Over here you plug in 3, right? All of that combined together. In general, if we would talk about just a function, now we just purely mathematics. No more application, no more lines, no more tangent line, no more velocity. Purely a function. We want to learn the behavior of that function at any point, not just at one point. We do the same process above, which is a limit of the different quotient. And that limit of the different quotient, limit when h approaches 0, limit of the different quotient, f of x minus f of a plus h minus f of a divided by h. That limit of the different quotient is written like this. This has a specific name, derivative. And that is the true definition of derivative. Derivative at a point. Okay. And this notation is written out like this. Read out loud like this. F prime of A. Prime. That notation is called prime. This right here, that's hyphen. F prime of A is basically derivative of F, derivative of F at A. What does it mean? The behavior of F at A. How do we find that? It's just a limit of the different quotient. Okay. Any question? Okay, so now we're going to be more theoretical, no more application. Those two examples both, that's the application. This is more theoretical, okay? So up to this point, when you ask, okay, now instead of asking you phi tangent line, phi velocity, just purely phi derivative. Now you should understand phi derivative, you put the limit in front of the different quotient. And for now, up to this point, phi derivative, your only option is this limit formula right here. Okay, not the derivative formula yet. And I'm sure most of you know the derivative formula. I think you know what I'm talking about. Most of you know this, right? Most of you learned it. Most of you saw that, right? Okay. But do you understand why is that? Why is some derivative of x squared is 2x? Why from here jump to here? What happened right exactly in the middle right there at the equal sign? What happened? The thing that happened is right here. This is the thing that happened. That different quotient. The whole process that you did. You did two examples. A lot of things going on in here in the middle to go from here to here. And we actually did that. Very big two example right here. One. What happened in the middle? That. Another one right here. Okay. Later on, you're gonna see that. Oh, y prime technically 3 over x prime, basically negative 3 over x squared is the answer down here. Okay. You're able to do this, but not now, not today, not yet. Right now, we still want to understand what happened right here. That equal sign, that simple step in this page. Right. Okay. So this is the result. We're gonna use that to check our answer. But what would be the process in the middle there? Okay. So let's do that. Let's apply the limit definition. Phi 1 by 1. Okay. Phi f prime of a for this function. In other words, phi derivative of f at a. Right, phi derivative of f at a. What f? Right here. Okay. And I think it's good that you know. Very good that you know. Everybody can see that. I hope. No? It's okay if you don't see that. We're going to learn that. But some of you know this. Right now. But that doesn't give you credit, not yet, for this. At this stage of the class, that is correct answer, but without explanation. Okay. Then why do I get from here? That would be my answer. That's basically my answer. F prime, that is my answer right there for this problem. But how do I, that arrow, what happened with that arrow? That's what I'm looking for. That is what we're looking for. And how do I set up that arrow? Limit of the different quotient. Okay. Actually change that to a to make it consistent. There. Okay. All right. So you have this. You write out a different quotient. Now you plug in everything in there. Okay, simplify that one more time. Practice that. Simplify that. Eventually, you should end up with this. Okay. And now, okay, back a day. Okay, before today, you may don't know why. Okay, you may know from here to here. But I think that you don't know why you have this to this. Today you know. Okay, do it. Try that. Work in the group. Simplify that. To help you, start the first step. H approach 0. Okay, a plus h square minus 8a plus h plus 9 divided by h minus a square plus 8a minus 9. There, I help you set that up already. Simplify that. You should have over there. Plus, okay, good. F of 0, oh yeah, plug in. There you go. When you have the answer, compare with your neighbor right away. Actually, that's the answer, to be honest. That's the answer. Right. I wrote you the answer already. You should have that answer, 2a minus 8. Right. But you cannot write that down like that yet. Eventually, in a couple more sections, or 1 or 2 more sections, you're able to do that. But for now, do the limit, do the halfway. Okay.
Organize and then you can just do everything at once. And
Everyone, do you see that minus, that plus, and that minus? Okay. Minus, plus, minus. Why you have, when you over here, that is plus, minus, and plus. You see the opposite? Why is that? And that's a very common mistake I see a lot.
But you're subtracting f of x?
Right.
Or f of it?
Yeah, when you're subtracting, you subtract these terms, right? You subtract all of them, right? So subtract, change the sign, that's why. That minus, right there. Okay, all right, so now, one of my favorite step when doing this problem is this right here. I'm able to cancel out a lot of things. If you're on the right track, you're able to cancel most of them. All right, it's just a bunch of opposite side. And then I see there's edge here, edge down there, and one edge up here. Okay, another edge over here too. Ooh, a lot of things to cancel. All right. So that just limit edge approach 0 of h plus 2a minus 8. Right. This h, that's 2a, this negative 8. Everything else gets cancelled. Plug in 0, now I'm able to plug in 0. The goal is that edge is gone. The goal is eliminating this edge, it's gone. 0 right here, 2a minus 8. There you go. Check. All right. So from now you understand why you have this to this, right? What happened right there? That simple arrow right here. That simple arrow. A lot of things happen in the middle. Okay. For now, for your exam next week, don't just write this. Okay. Even though you know, but write that on a scratch paper on the side. Okay, that would be my answer. Later on, I'm going to use that. My answer is going to compare to that. But what do I need to write? You know, that. Okay, that is actually derivative. Okay. All right. I think you can find the rate of change or how fast the function moving at 0, which is negative a, and so on. I'll let you finish that problem, right? Okay, another one to practice, but they basically the same. Okay, notice, look at this one. Find the tangent line to the parabola y equal x squared minus ax plus 8. Y equal x squared minus ax plus 8. Same problems, right? Basically the same problem. Different question, that's it. Not really different question. Same question, different wordings, right? This phi derivative, aka rate of change, aka how fast, aka behavior, aka slope of tangent line, right? Right. Now it's represented at least 5 things. 5 things you can use to say to describe this. Right. So now you find tangent line. The first thing you're looking for is the slope. The slope is the limit or maybe f of x. At this time, a or x, it doesn't matter. It's just a notation. Right? And from previous example, we're not going to do that again because it's the same problem. Same formula. That is the slope. This is the slope, this is the slope. And everywhere. Okay, that's the derivative. Okay, and now, you have another notation for this. That is derivative at a, aka derivative at x. See, many things to write out in one line. M, the slope. Okay, and this one more time. Velocity, no, not prime. There. Velocity, slope, right? X, A, derivative at A, derivative at X. They're basically the same, carry the same meaning. Okay. All right. So I have the slope. Okay. At everywhere, slope everywhere is this. I want the slope at exactly 3, -6. So at 3, -6, my slope gonna be, which number I'm gonna plug in? 3. X, Y, right? I'm picking the X. Slope -2. I think you can close out this problem, right? That is slope. Close out a problem with this point slope formula. Okay, finish now. I see you right here. Okay, group 3, what do you have? Do you have a B? Do you have B? Group 3. What's your answer? What's your final answer? I see that you shake your head. Go ahead. Same answer? Okay. Any other one have different answer? Okay, so I trust you guys here. Pause. Okay. Moving on. Derivative as a function. I try to blend this section with the previous section. This section, you're gonna learn, visualize what is the derivative look like, the function of the derivative look like. Okay. Normally, you know the function f of x. For example, f of x is, if I roughly draw that, a parabola. Let's say like that, x squared. Then you find derivative. You have 2x. It's going to be like that. Right. 2x straight line like that. Why? Okay, you understand that? You understand from here to here. You understand from here to here. You do the limit of the different quotient. Algebraically, it's like that. But from here to here, why the parabola turn into this? Okay, that's what it is section for. But in order to go to the visualization, we have to establish some notation, okay, to be consistent. In 2.1, we develop the derivative at the point A is the limit of the different quotient. I think by this time We've been writing this formula like 20 times already, maybe. A plus h minus f of a divided by h, right? Okay, like I said, A is defined as specific point. That formula, when you have A is defined as specific point, if you want to know at every point or everywhere, let A approach x, that means you just change the notation. That's it. A represent derivative at one point, x represent derivative everywhere. Okay, so we're going to start using this. Okay. All right. Sketch f prime. Okay, I'm going to show you how you're going to sketch derivative. Let me pick a very simple one. Let me pick a very simple one. Let me pick a very simple one. Just a single horizontal line. What will be the equation of this line?
Y equals 0.
Y equals 5.
Oh, I just said the derivative. Sorry.
Oh yeah, the derivative will be y equals 0. Y prime, y prime. If you say derivative, then y prime. Okay, it's going to be 0. Okay. So on the left side, for the following example, on the left side, you're going to see the original function, f. On the right side, I will try to sketch the derivative of that. So x still the same. Okay. If I use this formula right here, y equal 5, or technically f of x equal 5. I plug this one right in here, in this formula. What do I have? If I plug this one in here, okay, you're going to see a lot of, you think you're going to do calculation, a lot of calculation, but right? But the calculation for this particular problem, very simple. F of x is 5. So 5 here. F of x plus h is it 5 plus h? Is it this? No. If you have the x, if you have an x, then you replace to the x. This one, you don't have an x, you just have a constant function. So you don't have an x to plug in x plus h. You don't have anything here, right? You still maintain to be number 5. Okay, understand? Okay, you don't understand. I developed a technique to recognize a fake knot and honest knot, bunch of fake knot. Okay. Agree? Agree? Agree?
Yeah.
What do I do with this?
Take out the next stage.
Right? Right? Okay? All right. So 5 here minus 5 here. That's 0. I don't even look at the denominator. That is 0. The derivative will be 0. How do you draw a function that is 0? So from this. Okay, so I'm going to draw something 0. F prime equals 0 on the right hand side. You can draw a parabola, you can draw a line, you can draw everything, right? You can draw multiple, you can draw a cubic, you can draw an absolute value, you can draw many things. How do you draw 0? Yes, of course. First of all, let's establish, is a line, is a curve, is what? Is a point, is a dot, is what? What is it? Is a line, correct? Where? The x-axis, y equals 0, that is the one. Y prime or f prime equals 0 right there. Basically the x-axis. Okay. Okay. Now let's pause a moment. Analyze this. Very basic case. You have a constant function. A constant function. Keep in mind the word constant. Pay attention to the word constant. Okay. Pay attention to the word constant. You have a constant function. Now my question is, how fast is a constant function moving? Okay, let's say this is the span of the life of this function. Start its life, it finish its life. Along this line, does it ever change?
No.
Right? It never changed anything. Okay. Look at this with respect to a line. With respect to a line, as a line. This is a line, a horizontal line. What would be the slope of this line? A flat line. Okay, now it's a flat line. What would be the slope of this line? 0. Again, also look at this as a line. If I draw like this, it is increasing. If I draw a straight line like out there, it's decreasing. A flat line, not constant, don't increase, doesn't increase, doesn't decrease. Therefore, the rate of change, the derivative, 0 everywhere. See? Make sense? Okay. Okay. Next one. Y equal, or maybe f of x equal x. Okay, f of x equal x. So this is f, this is f prime. If you plug in the formula above, you do the limit, blah, 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 you're going to find out that f prime going to be 1. It's going to be 1. Then over here on the right hand side, can you draw f prime equal 1? What would be like? What will it look like? What does it look like? A line at
1, y equals 1.
yes, correct. Y equal 1 or f prime equal 1. Yeah. There. Okay. So the slope here, first of all, the slope remain to be, okay, the slope of this one is 1, right? Right here. It's 1. The slope is 1. The slope is also the derivative. The slope is 1. Derivative. Okay. This function increasing at the speed of 1, right? The slope increasing at the speed of 1. There. Parabola. A parabola. Can you work within a group? Within your group? Try to visualize what would be the derivative of this.
We have tangent lines.
Try that. Work in the group. Draw that. Okay. Okay. Go. Let's go. Let's try that. Try to plot this one. Okay, the derivative. What does it look like? Okay, let me go around and then show me your, okay, which group, just show me one, representing, which one? Okay, not enough, correct, halfway, not enough, not enough. So think about that, correct, but like 50%. Okay, what do you think, what did you draw?
I said it was probably 2x, but
2x, but how do you draw that?
oh,
Draw that, draw. 2x, everybody know that's 2x, draw it. Okay, also half, correct. Half. That means you're missing the other side. Okay, the other side. Nope, not absolute value. Nope, nope, nope. First of all, it will not be the same. So if the curve like this, your derivative will not occur like that. Okay, we're not first. Yes, I see that tail. Correct, correct. Yep. Okay. Okay, half correct. This is correct. That is correct. The difference is the tails. You need to get it along. There, yep, I like the arrows. Yep. Pull it longer. Because over here on this side. How about you guys? What do you have? There you go. How about you guys? Longer, pull it longer. You have the tails. Okay. So everybody know, okay. You guys are very quick at taking the derivative. Everybody know that it's 2x. Okay, because of our derivative formula. Okay. Then you draw this. Like 100% everybody draw this. The first part, that's A prime. Which is also correct, but half correct. Why is that? That represent, okay, this part right here, after 0, 0 right there. So starting 0 right here. It tell you that, okay, this function clearly after 0, look at the curve. You remember, you are not trying to mimic this plot visually. You try to mimic how this one behave. So after 0, think of this, is it going up or going down or going flat? Think of it in that perspective. It's increasing, right? It's going up, increasing. So therefore your derivative should also decreasing, right? Increasing, increasing. But before 0, 0 right there, before 0, this curve, what is the behavior of that curve? The tendency of that curve.
It increases, its y value increases while its x value decreases.
I think you said it backwards.
Backward.
The
Y decreases.
Why?
No, the y
Decreases,
while the
right.
x decreases.
Yeah. So it's, after this decreases. Earlier, right? The sign of the derivative tell you it increasing or decreasing. So the derivative positive. If it increasing, the derivative is positive. That is positive right here. 0, positive. Everywhere in here is positive. Because this one increasing, 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 increasing. That's why it translates to the positive. Before 0, your function flowing down, decreasing down. Decreasing give you the negative sign. Okay, so far good? Okay, so that's what I'm looking for, the second half right here. This one tell you this. Okay. All right. D. Okay, so I put it like this. So that's mean I want to make it look more dramatic. Okay, I'm gonna go above and beyond, huh? Okay, maybe this. Okay, the pawn, that pawn right here, where the flat, the pawn at the flat right there. Maybe give that 5. That is 2. That is 10. Okay. Now, something like that. Work as a rook. What would be the derivative of this one look like over here? Okay, try that. In order to do this, I need you to fill in 3 blanks. What would be f prime of 2? What would be f prime at 5? That means the speed, the behavior, the derivative of that function at these number. That basically the plot, you're able to locate this pawn in here. You get the idea of what this one look like. Okay. Try that.
Yeah, what's the function of this one?
Oh, there's no one function. You just try to sketch it. You don't need to know more function. Now this is not about finding the derivative. Don't try to find a formula. Don't try to think about x squared and then check 2x is a line. No, you don't need that anymore. Just represent by the increasing and decreasing of each interval.
Oh. 2 is probably 0. 5 is probably 0.
Those 3 numbers, 2, 5, and 10. What happened there? What happened here?
You change direction.
You change direction, that's one thing. Okay. I want to look at that in terms of a tension line. Okay, put a tension line at those points. Try that. Draw a tension line at those points. Draw a tension line here, there. Not really here. These 2 first. I don't need this. So technically, just I don't need number 10. Just 2 and 5 is enough for you. 2 there. 2 and 5 is enough. Just draw a tension line at 2 and 5. And then give your comment. Basically, I don't need number 10, to be honest. You can draw 10. 10 is irrelevant here. It's just a little bit abundant. 2 and 5 is enough. Okay? So if you draw correctly, that would be your tension line in the first point, right? That, 2, 5. Yeah, tension line there. 2 tension line. Those tension line is what?
0.
Constant. 0. Correct? Okay. It's okay. So you have those 2. That basically, when f prime, the derivative, when x equals 2, that is 0. When x equals 2, your derivative will cross here, will cross x-axis. Right. When x equals 5, right there. So whatever you draw a curve, you're going to cross this, or cross this, and then cross this again. Okay. I'm going to give you the first interval before 2. B equal 2. Look at this. B equal 2. Focus on this one only, this blue one. What is the behavior of that blue curve? That blue curve. What is the behavior of that blue curve? Decreasing. Decreasing. What do you think about the sign, just the sign of the derivative of that segment? If you take derivative at every point in here, take derivative here, take derivative here, take derivative here. Just think about the sign, plus or minus. What do you think? Why? Correct? Why? You just tell me earlier.
Because it's decrease, the slope is negative.
Yeah, decreasing. Every time you put a tangent line, it's going to be negative. So you know that, okay, the derivative at every point in there is negative. And then you go to here, the derivative going to be 0, 0, 0. Okay, flat line. Then how do you draw it? You know that it's going to be negative. Negative down here. Negative, 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 negative. There. Okay. Now use that analogy. Think about the middle one between 2 and 5. And then after 5. Okay. Go ahead, go ahead. Yeah, correct. Not really beautiful, but correct. Don't try. Okay, when try curve, if this one is smooth curve, try to make it also smooth too. Right. Correct. Okay. So each group give me. What do you think? Okay. Okay, when you draw like this, it will be in terms of derivative. What do you think about the sign of that derivative?
Decreasing.
No, the sign of this segment. Because you're talking about derivative, so all of these points are negative, right? Mm-hmm. You go to here, that's negative, negative, negative. Everywhere in here, negative. But in here, between here, you say it's increasing. Mm-hmm. So between this interval, the derivative should be?
Positive.
Positive. Correct? Yes, after 5, correct. Mm-hmm. Think about this. Yeah, you get the same idea. Correct idea is go down. That's why you have negative after 5. So between 2 to 5, what happens? Increase. Right, increase. Mm-hmm. Correct. There you go. Good. Good. Mm-hmm. Increase. No, increase in here. But you only need to know isn't positive in here is enough. How do you draw something that's positive and then go back to 0? Okay. What do you have? What do we have in here? Which one was that? Correct.
Yeah.
Correct. Okay. So most of you get the first and the last one correctly. After 5, I also use the blue because it's decreasing. So I know it decrease, 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 decrease. Translate that into the derivative. As long as it decreases, it will be negative. You don't care what does it look like in here. Like I said, you're not trying to mimic this. This go down doesn't mean you go down here. You don't have to go down in here, somewhere in here. You just make sure that is negative. It stay in the negative. Like that. That's enough. It's negative. Negative, 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 negative. Draw something that is negative down there. Okay. Then, the middle, I will use purple. It increasing. Everybody can see that. Increasing clearly. Because increasing in the derivative, it has to be positive. It's stack 2. I need to draw that positive there. That basically 90% correct. It's positive, clearly. Positive. So positive there. However, look at this one. Right at this point, in terms of derivative, you are 0. You flat line, 0. You start increasing, right? Look at the slope of each point. The slope getting bigger, right? Bigger. However, tell me about the slope. It's 0. It's getting bigger. But what happened? Smaller, getting smaller, right? Smaller, and then flat out again, go to 0, right? 0 getting bigger. Smaller, flat out to 0. Right? That is enough. Right? Did you get that? Okay. Any questions so far? Not, to be honest, that is not easy to visualize. That's why you have homework, right? Let me think of something. Homework. So this section, the homework is not on Open Math, so you're gonna do it either on your tablet or on paper, then submit it in PDF. Okay. So the homework, the first one is this one. Let me start about pick a number. So maybe 1, 6, 7. Okay. Flat 6, go down to 6, go back to 7. Actually, go down to 6, go to 7, and down. So I give you the first hint is that the derivative at each of these points, 1, 6, and 7, the derivative of each one of them will be 0. Okay, just based on that, draw these each interval. Don't worry that they are above or below the x-axis. You only worry about here that is increasing, in the middle decreasing. Oh, very big slope, right? Very big slope. Drop down. However, getting slow down. Okay, flat out to be 0. Positive, getting bigger, but smaller, getting smaller to 0 again, and go to negative. Okay. So try that at home. And before we move on to the next example, let's take a break. Okay. Let's take a break. I'm going to come back to this. Let's take 10. Let's come back at maybe 50. Okay. 11:25.